Hello everyone, my name is Jinhua Liu, one of the authors of this work, The Midas Touch, Triggering the Capability of LLMs for ARM API Misuse Detection. This work is done by Yiyang, me, Kaichen, and Miao Qianlin. All of us are from Institute of Information Engineering, Chinese Academy of Sciences. Today I'm going to show you how we use LLM to detect ARM API misuse. First of all, I'm gonna explain what is ARM API. ARM API is the abbreviation for Resource Management API. Such APIs are usually used in pairs, which might be common sense to developers, and such pairs are always omitted or unclear documented. We reported some detected pairs to library developers. They confirmed our contribution. However, they also noted that they might not explicitly write freeing API for each function. Such a negative attitude may lead to a large amount of misuses, which may lead to memory corruption, denial of services, data leakage, and so on. Three traditional ways are applied for ARM API misuse detection. Automatic code analysis may lead 72.7% multi-layer nesting functions cannot be precisely identified. Keyword matching for API names misses 76.28% ARM APIs, and template matching method in documentation processing is incapable of covering all the libraries according to our experiment. API documentation contains vast information for API, which is a good resource for extracting ARM API pairs, and recently NLP tools are the trending way for extracting API rules from documentation. However, such methods cannot handle constraints with neutral sentiment, and they are incapable of detecting API pairs across various sections or pages. Here are two APIs from different pages. The left one contains malloc semantic, and the right one contains free semantic. However, both of the descriptions are neutral sentiment described and they locate in various pages. The current API methods cannot perfectly handle them. Therefore, we are eager for advanced tool on API document understanding. With the advent of large language models with superior natural language understanding capability, we wonder if LLM can help us deal with the obstacles exist in traditional methods. And yes, the LLM can handle complex sentences with complicated information. However, new problems were dragged in. First, it fabricates answers without expertise. For example, if we ask LLM which API is used to free the malloc API EVWatch new, the LLM answers EVWatch free. This answer has the same naming convention and contains seemingly reasonable operation free, but this API does not exist. It's probably because LLM doesn't contain much information for these specific APIs. We also find LLMs introduce incorrect answers with evidence. When we offer the description of the free API zip discard, containing releasing semantics to LLMs, the answer is totally contradictory to the sentence itself. Therefore, solving these problems are the keys for precisely ARM API misuse detection. Our method, Chain Detector, deploys complex task decomposition to divide the complex work into three parts: ARM API identification, ARM API paying, and ARM API misuse detection. With the external information from API description and function definition, our method achieves the end-to-end ARM API misuse detection. In ARM API identification, we decompose the task into ARM sentence identification and allocation API identification. We also deploy two-dimensional cross-validation to confirm the correctness of LLM's output. For each task, we ask LLM to output its answer, evidence, and the reasoning process. For LLM's answer, the prompt contains binary classification, asking if there exists a sentence describing the semantics of the API, which is an open question answering approach. Take the API PCAP find out DVS as an example. The documentation shown in the right contains lots of information. The API name, function definition, description with 20 lines or more, which are difficult for traditional NLP tools, even QA models, to pick the related sentences. However, LLM can precisely identify the RM sentences among all of the information. We also need to verify if the answer is truly correct. Thus, we ask LLM to output the evidence which is retrieved from the documentation and follow the in-context answering way. Also, take the same API as an example. The evidence is consistent with the answer output by LLM. Since LLM is good at reasoning, we designed the prompt template as follows. Take the task to identify allocation API as an example. First, we ask a binary classification question to check if the current API performs allocation. Then we ask for the evidence, which is a double check, together with the reasoning process. We finalize the semantics of the current API. And the algorithm for cross-validation is shown in the left. We first ask for the allocated object by this API and check does it exist. Then we ask which API performs allocation to see if the answer is consistent with the current API. Finally, we check if the current API performs allocation. 3 answers are combined together to validate the semantics of the current API. We find directly using LLM for releasing API identification will cause incorrect semantics identification. And it seems LLM is confused of parameters type and name. Based on the observation that ARM APIs share common ARM object type, together with an off-the-shelf NLP tool, we pre-process the function definition and classify the semantics to precisely pair the ARM APIs. We also decompose the task into RM object identification and releasing API identification. For function preprocess, we find LLM is hard to identify parameters type and name when they are combined together. To solve this problem and to assist accurate bug detection, we pre-process them into structured format with index numbers, parameters type, and parameters name. 0 represents return value, and 1 represents the first parameter of the API. We supply the object description and function definition to output the RM object type. LLM outputs the correct type together with its index number, which indicates it is the first parameter from the function definition. We also supply the allocated object type and the function definition to output the releasing API. For example, given the object type pcap_ft and the function definition, the LLM correctly output the releasing API pcap_free or DVS for the malloc API pcap_find or DVS. For ARM API misuse detection, we apply the popular static analysis tool CodeQL. We manually construct the QL code, which can detect 3 types of security issue: memory leak, use after free, and double free. Such security issues may lead to denial of services and memory corruption. The detected bug in the right part shows in line 2537. The parameter all DVSP are mallocated by pcap_find or DVS. However, line 2540 missed the releasing operation to this parameter, which leads to a memory leak. Another detected pair is avdict_set and avdict_free. From the documentation and the source code, we find avdict_set performs allocation, which need to be freed using avdict_free when the program ends. One of the bugs is found as shown in the right, and the code snippet missed calling avdict_free to free the allocated object by avdict_set. 21 memory leak bugs like this are found in one popular software. Besides, we found some incorrectness in documentation. In the documentation of avget_token, it's clearly documented that we should use avfreed to free the mallocate string. However, this API doesn't exist and will cause false positives in previous work. We applied chat detector in 6 popular libraries and found 165 ARM API pairs with 115 security bugs as shown in the right part. When comparing with mature work, chat detector identifies 47% more ARM sentences and 80.85% more ARM API pairs. Besides the basic malloc-free pairs, chat detector can handle 22 types of ARM API according to their operation, such as set, open, create, initiate, and so on, which indicates that the initial keyword matching method for detecting ARM APIs is limited in performance. We also investigate the effect of different document quality on ARM API misuse detection. The results show that its performance has great difference between with document and without document. However, it shows slight difference among various qualities, which implies it's robust to document quality. With the advent of LLM, which tackles the bottleneck of traditional NLP tools on document understanding, in the future, people are encouraged to utilizing LLM for advanced security research. Thank you for your attention.
Okay, if anyone has a question, please come up to the microphone. And while that's happening, I have a question for you. So, did you report these bugs to these different library maintainers, and how did that process go if you did?
Yes, we report this bug to the maintainers of the software, and we also provide a patch for them to fix the bug.
Did those patches get applied, or do you have any idea how many or where they're at or anything?
I think some of them are confirmed, but I don't know the exact data, so maybe you can find it in the paper.
Oh, okay. Okay, and I have another question. So it looks like most of what you're applying this to are basically memory allocation and deallocation. Is this technique more general? Could this be used for other types of resource management, seeing if you're leaking certain types of descriptors, or if you have locks or things like this that you acquire a lock you never release when you're supposed to, or things like that?
I think we didn't do some experiment to prove that, but I think it can be extended to other types of API pairs. But I think the prompt needs some modification because we use the malloc semantics in the prompt. So if we want to detect the lock, unlock, for example, maybe we should change the malloc semantic to the lock semantic.
Okay, perfect.